Okay. Let me share my screen. Share. I didn't open my module slide. Open this slide. Let me open this. Just a second. Need to log in my server to get the PowerPoint slide. All right. In our last class we talked about the file allocation method, and we have seen the file allocation method for latest one. Last class we have seen the file allocation method by using this fat table, file allocation table, and you know that if you use this fat file allocation table, you need to maintain this very big fat table always inside the computer's RAM or memory. So it is kind of unnecessary. Then we have seen that if you use the file allocation, if you consider the indexing method, index allocation method, file allocation method, index allocation method means that in every file it contains a index table. It contains an index table, and index table actually nothing but is index table. Number of entry inside the index table depends on the number of file block inside a particular file. It's a file F1 contains total 4 blocks, 0, 1, 2, 3 blocks. So for this, when you save this file F1, this file F1, it will for file F1, your operating system will create an index table for file F1 as well. So how many entry will be the file F1? It will be the total 4 entry. 0 number entry, 1 number entry, 0, you can say 0 index, 1 index, 2 index, and 3 index. So this is 0, 0, 1, 2, 3. So for this 4 entry, we have total 4 index. So 4 entry will be the file index table. This is file index table. So what you need to do, so 0 number, and then what will be the 0 number entry? 0 number index will contain 1 number index will contain, or 2 number index will contain, 3 number index will contain, and what will be the value inside this index table? This value is nothing but the physical location of this 0 number block, and then physical location for this 1 number block, and physical location for these 2 number blocks, and physical location of these 3 number blocks will be here. What is the physical location? Physical location is nothing but inside this block address. Okay, block address. This is file HDD block, and it is called this. Its address is called 0, 1, 2, 3, 4. Let's say 5, and then 6, 7, and 8. That's it. And you know that depending on your HDD size, there inside your HDD, there could be millions of blocks. Now let's see the zero number block of this file. Zero number block is this file is stored inside this block number 1. So this file index table zero index will store this number 1. And then let's see this 1 number block. This is also known as this logical block address. Okay, this is logical block address, the block address block for logical block address. Logical address block address. And this is the physical block address inside the HDD is called physical address. Okay, physical address. So, and then 1 number logical block, let's say this logical block was loaded in block number 3. So here this file index table will contain this block number 3 in here. It will write this block number 3. 3 will be the entry for this 1 number index. And then let's say this block number 2 is loaded in 7. So here the entry will be the 7, and then last one is block number 3. This block let's say loaded inside this block number, let's say 5. So here this 3 number index index of file index table will contain the block number. Here it contains this block number 5. All right. When you read this file, then what will happen? So this file index table also needs to store inside a HDD block. Of course, this information is very important information when you read or write a file. Okay. Once you save this file, it is saved. Okay, it is fine. So we always open this file. Also, we always edit this file. Also, read this file. So this should be this file index should be permanently stored inside the HDD hard disk drive. So where it will also store? It will store some blocks inside some hard disk block. All right. Let's say this file index block. This file index blocks F1 is kind of this within this entry. This is 0 number entry. This is 1 number entry. 2 number entry. This is 3 number entry. Okay, this entry here is this 1, and then 3, 7, and this is 5. Means that 0 number block of 0 number block for file F1 was stored inside this block number 1 at the physical block number 1. Here 0 number was stored, and here this entry means that 1 number block of file F1 was stored inside this block number, inside the hard disk block number 3. And similarly, 2 is stored inside this block number 7, and 3 number blocks of file was stored inside this block number 5. Okay, block number 5 in here. Okay. Also, you know that this should be stored inside, let's say, this table, this file index table, this file index F1. This file index table is F1 index. Name is F1 index. This file index table should be stored inside a hard disk block. Let's say this block, this file index block is stored inside a block number 4. Let's say make it different color. In here this file block is loaded. This is file block. This information. Let's see only this. Yeah. Yes, this information is loaded. This table is stored inside this block number 4. Now let's see how actually it reads how actually your operating system reads this file F1. Also, you know that in every files it maintains every file. It has an entry inside a file directory table. There is another table is called, you know already, this file directory table. From the beginning, I just tell you, one is the file directory table, and this file directory table. What's the file directory table contains? File directory table is all of this file entry, or whatever file you creates in your computers, it has an entry inside this file directory table. And what's actually its contents? It contains the file name and file location, and then it could be file size, or whatever this information for file counter block, read write permission, and so on. Some others information in this table, but this two information is very important to read and write this file. One is the file name and file location. Let's say file F1, name is file F1 for this file. What is the file location? What is actually this file location will contains? In previously fat allocation method, as well as the some linked list allocation method, and some contiguous allocation method. This this file location contains the where actually zero block of file was stored. Let's say here zero block of file is stored inside this block number 1. So file location contains the location of 1 for the zero location for where actually zero location was stored inside a HDD. This block actually contains, and from there when you read this file F1, it searches by using this file name and F1, and it get this zero number block location. It is 1, and from this 1 it will just load this data, and linked list, by using this linked list method it can link to another blocks. Also fat method, from this zero number block is loaded at 1. So when from this 1 number entry of fat table, you will get this next entry. So always this method, in this method, it's this file directory table file location contains the zero number location of this file. But for file index table methods, it doesn't contain this zero number location of this file. It doesn't contain this file location. Actually, doesn't store this location, zero location of this of the file, zero location of this file. Instead, it store that where actually this file index table was stored inside a HDD block. So here this file index table is stored in block number 4. So your file location actually contains this number 4. Okay, when you read this file, or when you open this file, what's happened? At first, of course, when you open or read write, then it will check this file directory table to search this file. It is available or not. Then it will search by using this file name. So it will get this F1, and from this location, it will find this, okay, HDD location number 4, HDD block number 4 actually contains this file index table. So your operating system will take this whole data to the RAM, this table is nothing but this table to this RAM. So this table will contain sort of 4 entries, 0, 1, 2, 3, total 4 entries, 0, 1, 2, and 3, total 4 entry. From this zero number index of this table, it will get the zero number location of this file. So zero number block is loaded inside the block number 1. So it can read the data from this block number 1. And then from this, where actually one number block was loaded inside this block number 3. So 3 will be here, and 7 will be also here, and 5 will be here. And from this table, your operating system can read this every block of files. All right. So only difference is that this is others method, contiguous allocation method, linked list method, fat method. Inside a file directory table, file location contains the zero locations, zero block number of file where actually it was loaded. It was loaded inside the HDD. Inside this HDD block, this number was actually stored inside the file location. In case of file index method, this file location contains only the where index table. This index table was stored inside the inside the SDD inside the SDD block number. So here actually it's loaded this in our example, this F1 loaded inside the block number 4. So 4 should be in here. Okay, when actually it need read, then when you open this file, it will find this file number from this file directory table and get this index table location, and this index table will be loaded inside the RAM, and then from this index table, it will easily get this where actually 0 number block, where is 1 number block, where is 2 number block, and where is the third block. All right. Now let's see that when you are working with this file system, in fact, you need to always maintain this kind of very large table. Fat entry is kind of this total number of entry is equals to the total number of block inside the SDD. So this amount, if there is million number of block inside your SDD, so fat should contain this million number of entry. So this entry is always you need to load inside the RAM. But this entry actually refers this whole file information, actually whole block information. But at a given time, you work with only few 1, 2, or 3 files you open most of the cases. But in case of fat, you need to always this you maintain this overhead information. But in case of index file system, file indexing, when you open a file, just corresponding file index table will be loaded inside the RAM. You don't need to maintain kind of whole table or whole information for a SDD block number. So it takes, obviously it will take this less memory compared to the file block table. Also searching will be the searching will comparatively actually less actually easier than this fat table, because in fat there are lots of entry, but in file index table only few entries depending on the total number of block inside a file. All right. So it file index, if you use this file index method, index not file index, index allocation method, it provides some advantages as compared to the fat allocation method. So most of the cases nowadays we usually use this index allocation methods instead the fat allocation method. Previously, when hard disk size was small hard disk size, that time we consider this fat allocation. But nowadays the hard SDD size is very big, so in that situation we consider the index allocation methods. All right, and okay, let's see what will be the size of file index table. What will be the size of this file index table? We can calculate, previously we calculate the fat table size of this fat table. Now you can calculate the file index table as well. Okay, what is the size of this file index table for a particular file index table? How you can calculate? You can calculate these things. This entry is nothing but the address of blocks. Okay? Address of a blocks. Address of SDD block. Okay? Any address of this address. It can be let's say million. Of course, this is hexadecimal number, kind of this kind of number. Address of any hard disk block. This is kind of hex number, hexadecimal number. This kind of address, nothing but address. Okay. So what is the size of each address? It depends on the number of block, total number of block inside a SDD, inside a hard disk. Okay. What would be the entry for a single block? Now let's say how you can calculate the size of index table. Size of index table is nothing but, let me remove some part in here. So size of a table is nothing but it's very size of, let's see, size of a file index table. Size of file index table is equal to total number of entry, right? Total number of entry of this table multiplied by size of each entry. Okay, size of each entry. All right, now we can calculate this. What is the size of of a particular entry. Let's calculate these things. Size of each entry. So what is the size of each entry? Size this number of blocks depending on the total number of block inside a file. Okay, if it is more block inside a file, so number of entry will be the increase depending on the size of a file. The size, if file size is big, you know this is a block is nothing but 512 byte. Most of the cases 512 byte is block. So if it is depends on your file size, this number of block will be the increase, and also the number of entry for file index table also will be increased. Okay, so see this is how we can this is the total number of actually entry for this block. It depends on the size of a file. Also, you need to multiply by size of each entry. This size entry, but it depends on the total how many block inside your hard disk. Let's calculate if it is 512 GB hard disk. If it is 512 GB hard disk, and each block size, each block is 512 byte. Okay, so how many block will be there? 512 GB divided by 512 byte, which is nothing but 2 to the power 39 divided by 2 to the power 9 equal to the power 30. 2 to the power 30 blocks. Okay, if it is 512 GB and block size is 512 byte, you have total 2 to the power 30 entry. So what would be the size of a particular index table entry? It is nothing but a address hexadecimal address. So let's say how many bit is required in how many bit is required to making actually to addressing for 2 to the power 30 blocks. 2 to the power 30 blocks. How many bit is required? There is a formula like it is nothing but log of this cell, log of 2 base 2 power number of blocks. So here is 2 to the power 30 blocks. So it is kind of like this. This kind of bit is required for addressing every blocks inside this hard disk. So this amounts of bit size is for this is entry. Okay, bit size, number of bit. What is the size of this number of bit? This is the size of this is for each entry for file index table. So it requires 12. This is log of 2 is kind of 1. So you need to about 30 bits. This is not a byte, it is bits. If you divide by it 8, then you will get this byte. 8 bit equal 1 byte. So it is nothing but it's close to 4 bytes. Okay, so each entry is close to 4 bytes. Here is total here is total. Let's say in this example we have total four index. So each index is around each index size is around 4 byte. So total 4 into 4, we have total, this size will be the total 16 byte. And this table, this 16 byte table should be always stored inside the HDD. In our case, we consider this table was stored inside this block number 4. So you see this is only 16 byte. Here is 5, this block size is 512 byte. There is only 16 byte. So rest of them byte is kind of wasted. Only few part will be the here, few part will be the is kind of like this. In block number 4, if you loaded this file index, only few part will be there stored, and rest of them part will be the wasted. It will be wasted. It is also known as the internal fragmentation problems, right? Internal fragmentation problem. It's also known as this internal fragmentation problems. Now let's see. It is fine. If this size is, if this index file size is less than a block size, then there will be some internal fragmentation problem. But what if this block, this size, this file index size is greater than this block size? Let's say you have a file index table, and then inside this file index table, you have lots let's say at first think about you have a very big files, and it has lots of entry, lots of block, very big file, and it has lots of blocks. So your index table, file index table will be increased like this, and its size is entry size. You know that is entry size is nothing but around 4 bytes. Okay, we calculated here 4 bytes, 4 bytes, and let's say this size will be increased. Let's say 560, total 60 byte. This table size 560 byte. So also you know that each block size is 512. So 512 will be stored in here. What is the rest of them? The rest of them 48 bytes. Okay, 560 byte this table size, and then you 500 is then 512, and then you have rest of them. You have total 48 bytes. Okay, you need total 48 bytes. Okay, now let's see 48 bytes. So 48 byte, you need to store some another blocks. Okay, you need to store some, let's say this block number 0. You store this block number 0. So how you can actually how you can read this block number, and then what's actually file directory table will contain. File directory table will contain this file name. File directory table, before I showed you that file directory table. File directory table contain nothing but this file name as well as it contains the file name as well as the location and some others information. So here file name is f1. So here this and location, actually indexing method location, actually nothing but it's located this file. Where is file index table loaded? Here file index table is loaded in 2 blocks, inside these 2 blocks. So what's information here? It will store. If it is stored only this 4, then 4 will be the loaded. But some information is also stored in block number 0 as well. 48 bytes information was stored inside this block number 0. So when it's finally loaded this block number 4, so some block will be missing. Some block will be the missing in that case. So you cannot manage by using only the single level index. So you need to consider some double level index. How it works? It just works double another. You need to manage this another table. In that case, if it is this file size is bigger than this index table is larger than the block size, then you need to maintain some other level of index table. Its contents the zero index. Here is only 2 blocks is needed. So here is 0 and 1. Here is also due to 2 blocks, extra 2 blocks is need for this file index table. So here is need total 0 and 1, 2 entries fine. So first entry will contain this where this first of this part was loaded. First part was loaded, this block number 4. This block number 4. So 4 will be loaded in here. And then rest of this part was loaded inside this block number 0. So 0 will be in here. And then of course these two things is stored inside this block number. Also this block number also store this one. Also this one you need to store some block inside a HDD, one block inside a HDD. So this block, let's say it is stored inside this block number. Let's say this is block number 6. Okay, 6. Inside this block number 6, you store this level of indexing, this table, and then in block number 6, so 6 will be in here. So 6 will be then in here. So when you read this file, then from this block number it will load this 6 number entry. So 6 number entry, then your operating system load this 6 number first table, 6 number block inside this HDD, and from this 6 number entry there is kind of it contains some another block address. So from here it can see this first part of this file index table is loaded in here. It's just loaded this block number, every information for this block number 4, and then it will load this block number. What is the block number 0? So it's loaded in here, block number 0, and then you will get this all of this information. From this 0, so you'll get the 0 location of this file. Let's see, it's loaded in 19, then let's say one is loaded in 100, so you can read all of these files. Okay, all of this information for a particular file. So in here you can see, if you consider if you consider the if you consider uh, if your file index table is smaller than, if it is smaller than a block size, then uh, there will be the internal fragmentation problems. And if it is larger than this block size, then you need to go for another level of indexing. This is called multi-level indexing, indexing of a file table. Okay, all right. So these all for file indexing methods. Our next part is the next thing we have to learn this how you can manage the free space. Okay, free space, how we can manage the free spaces of a SDD, of hard disk drive. Okay, you know that if it is SDD drive, there are lots of blocks inside the SDD. So how you can maintain this free space, and then this is like this. Also, you know that we prefer the non-contiguous allocation. So let's say this block is stored some file, and here this block is stored some file. This is 0 1 2 3 4 5 6 7 8 9 10 11, and then let's say 1001 1002 1003 and 1004. All right, now let's say this block is empty, and here let's say this block is full. Here is this one empty, this one full, this one empty, and then full, kind of like this. Okay, it's kind of like this. Okay, now how actually maintain this? Here here is one hole, here is empty block, here is also empty block, here is also empty block. How actually HDD maintain this kind of empty blocks inside a HDD drive? Okay, here is two methods actually follow to manage this empty space of hard disk drive. One method is called this bitmap methods. One is called this bitmap methods. But in two methods, you can any of them you can go. One is this bitmap method. Another method is known as the linked list method. Okay. Linked list method. What is the bitmap method is what? At first, we talk about the bitmap method. Number one is bitmap methods. In bitmap methods, nothing but it maintains a list. It maintains a very big list, means that is kind of like this, and then like this. Okay, it maintains a very big list. The number of entry in this list depends on the number of block inside a SDD. If it is 2 GB, there is 2 to the power 30 blocks. You already calculated. Is 2 to the power 30 blocks. So if it is 512 GB hard disks, 512 GB hard disks, then this amount of block. So list will contains in case of bitmap methods. In case of bitmap methods, this is bitmap methods. In case of bitmap method, this list will contain total 2 to the power 30 entry. Okay, like your head table, but here this entry is only single bit. Here it will contain this only single bit, either 0 or 1. 0 1. It's only single bit. So this size is small, very small compared to the fat table. Okay, so bitmap maintain a list, and list contain this list contains the entry which is equal to the total number of blocks inside a HDD. So either this what is the value for each block inside a list, the block inside a list is contain either 0 or 1. 0 means this block is full, already occupied by others file, full or already occupied, and 1 means one will refer as the in this list, 1 is refer as the it is empty block. Empty block. Now let's see if you think about this example, if you think about how it looks like here is 0 number is full, here is 0 is full. In our example, we consider the 0 is full, so 0, this value should be 0, and for this here is 1 is empty, so 1 is should be 1, and then 2 is full, so 2 should be 0. 3 is full, so 3 is 0 here. This is let me numbering it. This is 0 number, 1 number, 2 number, 3 number, 4, 5, 6, 7, 8, 9, and so on. And then let's say 4 number have condition for this 4 number block. This is 4. 4 is empty, so 4 should be the 1. And then 5 is full, so 5 should be the 0. And that 6 is empty, 6 should be 1. And 7 is full, 7 should be the 0. 8, how about this 8? 8 is empty, 8 is 1, and 9 is full, so 9 should be the 0. It's kind of like this. So once your operating systems save a file, try to save this file, what it will do to figure out this free space, it will search this bitmap list, and it will see, let's say you create a new files f1, you want to save this file f1, and it has total 3 blocks, 0 number block, 1 number block, 2 number blocks. Then how actually it's figure out where it will store this block, at which physical block number it will take. Then it will search this bit table, and it will find that okay, 0 number block is already occupied, and then it will see that okay, 1 number block is empty, so it will just keep this 0 number block in here, 1 number physical block of HDD. Okay, let me make it. So here actually it will keep this one. It will be stored inside this block number 1, and then it will go through it will find this okay, 2 is full, 3 is also full, and 4 is empty, 4 is 1. So then it will make what it will then after store this inside this 1 number block, then it will update this bitmap. So bitmap here it will be the 0, 1 to 0, because it already stored, occupied by file block f1. Now again it continue to search, and then it will find this okay, 1 is 4 number is 1, means that it is empty, so it will store this block inside this 4 number, and it will make it 0 because it is full now. And then this 2 number block, and then it is searched again, 5 is full, and then 6 is empty, 6 is whole, so in here 6 will make it 0, and this 2 will be inside in here. Okay, this is how bitmaps work to manage the free space of hard disks. Okay, but in case of, there is another method. This method's name is the linked list method. Okay, let's see how linked list method work. Linked list method, we already see about the linked list allocation method, but it is different from this file allocation method when linked list used for the free space management. Let's say how it works. Linked list, let's say in previously here this block is empty, this one was empty, like this one empty, it was also empty, okay. Now your linked list will, the first empty block, it has a address, where is the next empty block, it's point to the next empty block. The next empty block is 4, so it will point to this empty block, next empty block, and then next empty block, this empty block will figure this. Here is also address, one address. This address is nothing but where is the next empty block. So this address is point to, actually point to this block. Okay, this block, this is the next empty block. So here is maintained one pointer. This pointer refers where is the next one. This next one is in here, and then this block will point to where is the next, and this is the next. Okay, this is the next, and there, and so on and so on. This is how linked list work. What actually during the save operation, what's actually your operating system will do? Your operating system, let's say you want to save this file f1 again, it has total three blocks, 0, 1 and 2, total 3 blocks for file f1. Let's say your operating system at first will be loaded the first empty block address. So first empty block address is nothing but 1. This is 1. So from here, this is this thing. This is inside the RAM. This thing is referred as this first empty block address. Okay, this thing will be always inside the RAM. Empty block address. Then what it will find? Okay, it will find this. Okay, one is this. There is also one block in here. 0 number block wants to store. So here is also one block in here. Here is also this 1 number block is empty. From here it will get. So it will store this first block inside in here, and then it will just remove this link, and then it will find this where is the next empty block. So next empty block is 4. So it will be next empty block will be the 4 in here. 4 will be here, and then it will, from here it will take this where is the next. So next is 4. So 4 it will store in here 4. It will remove every address and everything, and then it will find this where is next. Also figure out this next empty block is within the 6. So 6 will be here, and then from here 6 will be stored in here, and then next first empty block is 8. So 8 will be stored in here. It will be updated in here. So here is, you don't need to right now any link because it is full. So whenever whenever your operating system store the next file, it will find this next empty block is block number nothing but block number 8. So it will store this block number 8, and from this information it will get this where is the next empty block. So it will take this whole spaces, because you don't need to store this address anymore, because from this your operating system will collect this next address. So it will be in here, and then it will remove this. Your operating system will remove these links, nothing but remove the first entry from the linked list. Okay, this is how the linked list method works. Okay, both method is either linked list or bitmap. Both is can be useful to manage the free space of your hard disk drive. Okay. All right, that's all for memory allocation, as well as the memory allocation, and also free space management. Free space management is related to the memory allocations. In next, we'll learn the disk scheduling algorithms. So in order to continue with the disk scheduling algorithms, we need to know about the, at first we need to know about the hard disk structure, how actually one hard disk looks like. Okay, your hard disk looks like. In order to show this hard disk structure, I need to share it from my laptop PC. I need to share it from my laptop PC because it is a complex diagram. I'll show you. I cannot. At first, you need to know about the. You need to figure out this. Let me share it. Then you'll find it, that how it looks like, how the disk architecture is looks like. Okay, HDD drive is looks like. But I think you can see the screen. All right. In here, you can see that first, this is the actually HDD drives. if you look at inside this SD drive, there is nothing but CD-ROM type or DVD types platter over there. This is DVD type platter over there. This is magnetic disc. mm, Magnetic disc. So this DVD type platter is this DVD type plate is known as the platter of hard disk. So number of platters depends on the size of your hard disk, size of the hard disk. Okay, if it is 512 GB, I think there should be around 5 to 7 platter. Yeah, and if it is more, then platter will be the more inside your hard disk drive. And then next one is so this the platter. Platter is very important. Platter is magnetic things. In platter contains the large amount of track. Each platter contains a large amount of track. Okay, it's kind of this here. It shows this only one track. So this is the track. Also, there is track. There could be some thousand and millions of track inside a particular platter. Also in DVD drive, data is stored only a single surface. You know that in in uh, in the below surface, is the surface, in top surface there is no data is stored inside the below surface. But in case of SDD platter, data is stored in both surfaces, these surfaces as well as there is down surface. There is, you can see this is one surface, and there is below there is another surface. In both surfaces there, you can store the data in case of SDD plotter. Okay, in both surfaces there is data. This top surface and also below surface there is some you can store the data, not only a single surface. This is another platter, this is another platter, but each platter contains two surface. This is top, and then there is also the below surface. In top and below both contains the data, and each surface contains the large amount of track. Okay, and each track contains the large amount of block that actually I draw in the picture, that this is the hard disk block. This is the hard disk block. Actually, block is looks like that one actually is block. Here you can see this is the block. Here is its reference the sector. Sector is nothing but a block. Okay, this thing is block. So this block needs to read or write for a hard disk drive to store the data. And then there is a splinter. Splinter actually is rotate. It's always rotate. So disk is every disk is rotate. So splinter is connected to all of these disks. So it is always rotate. So disk also rotate. And then each disk contains in every disk every plotters contains the read-write header. Read-write header, nothing, and not a single. There is not a single read-write header. Each platter it has the read-write header. From here you can see this is the read-write header. So each platter it has this read-write header. Not only this side also one header, also below side there is also one header. Okay, read-write header. So this header actually read the data from the SDD platter. Okay, and so this number of read-write header is equal to the number of platters. Okay, if you contain this two is a one. This two is a one head, but this is here is the two head. So here is for three plate, there is requires 6 head. But if it is four plate, so there should be another two read-write header. Okay, there is one header, there is another header, and then these things is always rotate, and then if you okay, this is another thing, the cylinder. What is the cylinder? If you join this track number, if you join two track numbers between two platters, this is track number, let's say this is track number one, this is track number one, also this is track number one for this next platter. If you join these two tracks together, then it looks like a cylinder. Also, if you join this all three together, it looks like a cylinder shape. It looks like a cylinder shape. So this is known as the cylinder. If you have there is lots of track. So if there is one, this is, let's say this is one number track. Also here, let's say there is also another track. If you join this track, also there will be the another cylinder. All right. So this is the some configurations of HDD drives. So HDD main things is platter. Platter contains surface, two surface. In both surface there are many contains many tracks, and each track contains the sector or block of an hard disk. This is 512 byte that we actually I showed you, always I showed you when I draw these pictures. This is the sector, and then splinter actually spindle just rotate the this rotate this platter, or let's rotate this platter, and read write head read or write the data from the HDD block or sector. Okay, this is the some this is the actually this all for this figure. Let me stop share it and share it from my whiteboard. Let's see some others item from SD drive. Let's say you have this is one. If you consider this is one platter, each platter contains, this is kind of nothing but track number. If it is called, this is the let's say this is 0 number track. Each track contains the block that I actually write this way. Okay, this thing is nothing but here that thing. Okay, track contains this kind of block. Okay, this kind of block I showed you inside this kind of diagram, but it is nothing but inside a track. Also, this is one number track. It contains the same. It contains the more amount of block. Okay, because this is the large one. Outermost is also this track is very bigger than the inner one, so it contains some more block, kind of like this. Okay, the track inside here, this is called the innermost track. This is splinter is connected to here, and then track over here, it's called this outermost track. Okay, this is also content. Each track contains the number of blocks, a finite number of blocks. It could be, depends on your HDD size. There could be millions of blocks over there. Okay, kind of like this. Now here is kind of read write head. Okay, read write head. Let's see. Okay, let's see that your at the beginning. Let's say you have a file. You have a file that is let's say 0, 1, 2 total 3 blocks for this file. So file zero number block was stored, let's say in this block, and then one number, then actually let me this thing, the track. Okay, track, and then this block. Okay, here is also, of course, there is some block as well. Okay, let me this zero number is loaded in here, in this block, and then one number was loaded in here, let's in here, and then there's a 2 number is loaded somewhere in here, between here. Okay, if, and this is let's say this is 0 number track, this is 1 number track, this is 2 number track, this is 3 number track. All right, there could be some more track, thousand of track inside a SDD. Okay, now initially you read write head, also there is, to read this data there will be some read write head. Or let's read write head, read this data. Let's say initially you read write head, initial position read write head is in 2 number track. 2 number track is it just initially its position, read write head position at 2 number track. Okay, 2-number track. Now we want to read this file F1. So file F1 and its 0-number block wants to read data from the 0-number block. It is loaded inside the track number 0. But your read date head is now currently inside the track number 2. So your this read write head needs to move. At first, your read write heads needs to move till 0-number track to read this block. Okay, because this 0-number block for this file, this 0-number block for this file is loaded at 0-number track number 0. Some sector, some block inside a 0-number track. So this read write head, if it is read write head, this head currently in track number 2, so this should be moved at the track number 0. So from 2 to track number 0 comes to the move to the track number 0, and this way it's a move up and down like this way. It can move where also it can move down. Okay, move up, move down, can move around. So in order to move this track number 2 to track number 0, it needs some time. Of course, to move one head from track number 2 to track number 0, it takes time, some time. Okay, this time, the time taken to move HDD read write head from one track to another track, is known as the seek time. Okay, you need to understand this kind of parameters because we will learn the HDD scheduling algorithms next. So you need to know these parameters. What is the seek time? And then let's see some parameters. Okay, this is the seek time. Seek time is nothing but to move your, let's say your HDD head is currently in this 3-number track, and then it needs to move to 2-number tracks. So how much time is required from to take one track to another track? So this is called the seek time. So let's say your HDD heads needs to move one track to another track within 1 nanosecond. So seek time is 1 nanosecond. If it okay, so seek time is 1 nanosecond. So if it needs to move from 3 to till 0, so it needs to move 1, 2, 3, total 3 tracks. So it will be the total 3 nanosecond. It needs total 3 amounts of time for seek as a seek time. Okay, this is the seek time. To move, the time requires for the time actually needs the HDD read write head from one track to another track. This is the seek time. All right. Now let's see your HDD is moves from HDD head moves from this track to this track to 0-number track. This is the 0-number track. This is 0-number track is now your HDD heads in here. Now it needs to read the data from this location, okay, this block locations. So how actually it will read? It is now in here. So this HDD heads can rotate this way, only this way, this direction. It can actually explain that this direction. It cannot move. The HDD head cannot move. It just wait in here in his location. It just changes track. It can change this track only. But it cannot move this way. It can move this way. Okay. Now how actually read this? I mean here, how actually read this block number? So you know that Splendor actually rotate this HDD like this way. If it is rotated in this way, so after sometimes this block will be inside the HDD head. Okay, inside this HDD head. So from once actually it's inside this HDD head, your head can start to read the data. So to move this block from this place to that place, a read write head place, it takes it actually comes due to the rotation of hard disks, rotational of this actually platter by using spindle. Okay, so it comes to inside this hard disk, so it takes time. Okay, from if it needs to read from this location, so it takes less time. So it needs it reads from this location, so it needs to rotate inside this hard disk. It takes also time, but if it is near location, then it takes less time than the compared to the far location. So it takes time to be inside this hard disk. So this is known as this time actually known as the rotational latency or rotational delay. Rotational latency time, rotational latency or rotational delay. This time is so rotational latency or rotational delay is nothing but the block time requires time needs to block be inside the read write head. Okay, this is the rotational latency or rotational delay. Now let's see another thing is that once let's say this block, okay, this block is now here is here the first time it was close, so it is rotated, so now it is in here. This block is inside this here. This block is currently inside in here. So once this block is start in this location, so your read that head will start, your SDD read that head will start from this reading once it finds the starting point of this SDD drives. Okay, this is, let's say this is the block, target block. Once it is inside in this position, it will start. So if it is rotated this way, so this is the starting position. Your SDD head will read start from this starting position till there. Okay, it goes if it is moves this way, so this will be rotated in this direction. So it needs to store from this way, opposite direction, this way it needs to store. The SDD it will be stored from this side to that side because it's rotated this in this direction. So once it's inside this SDD drive, and then to read this data by read write head, it takes time. Even though it takes time, so it is known as the data transfer time. Data transfer time. Okay, here is three things you need to know. One is called this seek time. Seek time is nothing but the rotational time of one sorry, change time of SDD head from one track to another track. This is seek time. And rotational latency time takes the target block to inside the read write head. This is the rotational latency. Once it comes inside the SDD head in here, once it's inside this SDD head, then it's your read write head start to read this block. So to read this block or write this block, whatever read and write, exactly same way it works. To read or write this block, it takes some time. So this is called as the data transfer time. Okay, these are very important parameters in order to understand the disk scheduling. You know that if you consider this disk scheduling method, which needs the less amount of seek time, rotational time, or data transfer time, this will be the good algorithms. All right. So these are the basic of SDD structure and some parameters and time parameters of SDD drive. SD drives. So in our next class, we'll talk about some disk scheduling algorithms. All right. So for today's class, do you have any questions or comments for today's, or do you need anything to clarify or understand? All right. If not, we are almost running out of time today, so we can stop here today and see you next week, and have a great weekend.